The image appeared without warning, a pale smudge suspended against a starless backdrop, captured by a spacecraft that was never meant to witness anything like this. For months, astronomers had been straining to observe 3I Atlas as it whipped toward the sun, only to lose sight of it entirely when it slipped behind the solar glare during its late October perihelion. Yet in that blind spot, as Earth-based telescopes saw nothing but photon washout, ESA's JUICE spacecraft quietly aimed its navigation camera toward a patch of sky few people were thinking about. What it returned was the first spacecraft-side photograph of an interstellar visitor undergoing violent, possibly transformative activity inside our solar system. The frame is crude, taken by a camera built to keep a spacecraft oriented, not to redefine astrobiology. And still, this single image may end up symbolizing the most important encounter humanity has had with a natural object from another star system. The timing alone is extraordinary. When JUICE snapped its preliminary image on November 2, 2025, it was embedded in a narrow observational window, having drifted into a geometrically perfect vantage point just days after 3I Atlas reached its closest approach to the Sun. 2 days later, the spacecraft would make its nearest pass, about 66 million kilometers from the interstellar object. Far too distant for detailed mapping, but close enough to give scientists something they lacked entirely: confirmation from outside Earth's line of sight that 3I Atlas was still active, still shedding material, and still behaving in ways unlike any comet or asteroid ever documented. The sharp glow of its coma, faintly visible tails, and complex halo structure suddenly had a second set of eyes. Earth had telemetry. JUICE now had the imagery. By the time JUICE looked at it, 3I Atlas had already become the strangest natural object scientists had tracked in decades. Months earlier, long before it reached the inner solar system, astronomers noticed something odd in its light curve. As the object crossed 2.5 astronomical units from the Sun, it abruptly brightened by roughly 2 magnitudes, a dramatic spike that would typically indicate a brief cometary outburst. But in this case, the brightness never subsided. Instead, it continued increasing steadily all the way into perihelion, a behavior that suggested not a localized eruption, but a global state change across the entire surface. The conclusion many researchers gravitated toward was that 3I Atlas had undergone a cryovolcanic transition, a sudden, widespread activation of volatile material that had lain dormant for perhaps millions or billions of years. For an object that had not passed near a star in at least 10 million years, the first strong sunlight it encountered in geologic time may have triggered planet-forming chemistry on a scale no one had expected. This view gained traction when spectroscopic measurements began accumulating. 3I Atlas displayed remarkably high ratios of carbon dioxide to water, around 8:1, a 4.5 sigma deviation above what is typical for solar system comets. Carbon monoxide was also abundant, and while the interstellar object was rich in nickel, it was not depleted in iron, an important clue because the nickel-to-iron balance resembles that of Cr carbonaceous chondrites, extremely rare meteorites believed to have formed outside the protoplanetary disk of the early solar system. These meteorites contain metal-rich cores and abundant organic compounds. They also undergo a fascinating chemical process when exposed to liquid water. The corrosion of iron-nickel metal produces magnetite, Fe3O4, one of the strongest naturally occurring magnetic minerals. In laboratory settings and meteorite studies, this corrosion is known to drive Fischer-Tropsch-type reactions, which can generate complex organic molecules, including amino acids, sugars, and precursors to nucleic acids. Astonishingly, every major ingredient for those reactions appears to be present on 3I Atlas. As solar radiation increased, the interstellar object began releasing water and volatiles that had accumulated during its long journey through deep space. At around 2.5 AU, models strongly suggest that liquid water could exist transiently within subsurface pockets. If so, then the sudden brightening at that exact distance becomes more than coincidence. It becomes evidence that the object's crust, built from interstellar dust, ices, and organics, suddenly thawed, reacted, and erupted. For a body spinning every 16 hours,
solar heating would have been distributed evenly, enabling the entire surface to undergo transformation at once. This hypothesis was reinforced further after perihelion, when amateur astronomers and professionals alike began capturing images of spectacular jets streaming away from the nucleus, plumes extending tens of thousands of kilometers into space. Some exhibited wavy filamentary structures, indicative of plasma interactions, showing that the object was not only chemically active, but electrically and magnetically dynamic as well. Most comets develop a tail that points away from the sun, shaped by the solar wind. 3I Atlas, however, also developed a brightening sunward-facing tail, becoming more pronounced even as the main anti-solar tail dimmed. Few natural objects behave this way. Fewer still do so while exhibiting the chemical signatures of magnetite formation and metal-catalyzed organic synthesis. All of this was already known when ESA released the JUICE navigation camera frame, but the image nonetheless shifted the narrative. Suddenly, 3I Atlas was not a distant haze glimpsed from ground telescopes. It was a real, visible presence inside the solar system, photographed by a spacecraft that, as it races toward Jupiter, will not reach its primary target until 2031. JUICE was never built to chase visiting interstellar objects, yet by remarkable timing, it found itself ideally positioned to glimpse one just as it passed through its most important evolutionary stage. The photograph, modest as it is, confirms that the interstellar visitor was enveloped in a complex active coma at a moment when Earth could not see it at all. That alone makes the image historic.
What elevates its significance even further is the flood of new astrobiological contexts arriving at nearly the same time. NASA's OSIRIS-REx mission delivered samples from asteroid Bennu in late 2023, and throughout 2024 and 2025, laboratory analyses revealed an inventory of organic molecules that stunned researchers. Bennu samples contained all 5 nucleobases needed for DNA and RNA. They held 14 of the 20 amino acids used by life on Earth, along with evidence of ancient briny water and complex carbon-nitrogen compounds. Bennu is not a special object. It is an everyday B-type asteroid, and yet it contains the raw ingredients for life in astonishing abundance. If a processed, sun-warmed asteroid like Bennu can preserve such chemistry, then what might an unprocessed, interstellar, cryovolcanically activated body like 3I Atlas contain? The converging evidence has led several scientists to revive an idea once relegated to speculative astrobiology, that organic molecules, and perhaps the precursors to life itself, may routinely travel between star systems. This concept, known as pseudo-panspermia, proposes that complex but non-living molecules form in space and are delivered to planets by comets and asteroids. Bennu demonstrated that these molecules are not rare. 3I Atlas suggests they may be everywhere, that interstellar space may be full of dormant chemistry, waiting for a warm star to ignite it. As 3I Atlas approached the Sun, its crust likely released a dense stream of material, a mixture of water vapor, carbon compounds, dust, organics, and potentially magnetite-bearing grains. This material now forms a debris region behind the object's orbit, a region Earth will pass through in March and April of 2026. No one expects a light show. The particles are too small and too diffuse, but the moment remains profound. Earth will literally fly through the exhaust of an active interstellar body that may carry the very components from which life can arise. Meanwhile, 3I Atlas continues outward, fading slowly yet still shedding clues. It will swing past Jupiter in March 2026, its closest approach a reminder that interstellar objects can traverse our planetary neighborhood without warning. Beyond that, it will arc outward and return to the darkness between stars, carrying with it whatever chemical experiments the Sun triggered on its surface. Scientists will keep watching until it becomes too faint to track. But JUICE's fleeting image and the February 2026 release of its instrument data will provide a rare archive, the first near-spacecraft-level investigation of an interstellar object caught mid-transformation.
None of this proves that 3I Atlas carries life, nor that life can arise spontaneously on such bodies. What it does prove is more fundamental. The chemistry required to build life, amino acids, nucleobases, sugars, organic catalysts, emerges naturally from the interactions of metal, water, and carbon under the right heat conditions.
These ingredients accumulate over enormous spans of time in the cold of interstellar space, and when a wandering object finally approaches a star, the resulting burst of energy can rearrange those ingredients in ways that resemble the opening scenes of biology. The fact that we now have a spacecraft photograph of an object undergoing precisely that kind of activation is, for many researchers, transformative. This is what the JUICE image ultimately represents. Not aliens, not cosmic messages, not the arrival of anything supernatural, but something perhaps even more consequential. A glimpse of the machinery that may seed entire galaxies with the potential for life. In the faint glow captured by a navigation camera, we are watching an interstellar chemistry lab fire itself awake. Whatever we learn from this moment, whatever the data reveal in the months ahead, 3I Atlas has already altered our expectations. It has shown us that life's ingredients are not confined to solar systems, that the universe itself may be constantly mixing and redistributing them, and that our sun has the power to awaken that chemistry whenever such a visitor passes close enough. The image is small, its implications are not.